Okay, welcome back. So today we are going to continue with our continuous distributions, probability distributions, and we're going to discuss the exponential distribution. So this is going to be all about exponential experiments, random variables that follow an exponential distribution. Okay, so here is the characteristics or things that we can consider. Okay, so exponential distributions often concerned with amounts of time until a specific event. What other distributions have we? What other distribution have we talked about where we're interested in the first time that an event occurs? Well, think about discrete probability distributions. Didn't we discuss a discrete probability distribution where we have a certain number of trials until we get the first occurrence of an event? Or wait a minute, the first occurrence of a success? What discrete probability distribution did we talk about that was interested in the number of trials until we get our first success? It was the geometric distribution. So hold on to that. We're going to talk about that in a little bit. Okay. So, but in the exponential distribution, so in the continuous realm, right? So in the when talking about continuous distributions, when we want to talk about exponential, we're talking about the amount of time that passes until an occurrence happens. So an event occurs. Okay. So those are the types of questions that we're going to do. For example, the amount of time beginning right now that you would have to wait until an earthquake happens, right? That would be an exponential distribution. Or the length in minutes of a long distance telephone call lasts from the moment that you dial a phone number. Or the, the amount of time in months that a car battery lasts. Or the amount of time that the lights in this room will stay on once you flip the switch. Or the amount of time that your VCR will run as soon as you turn it on, right? Pretty much any electronics, right? The amount of time your computer will stay on until it burns out, right? When you turn the power on. All of these things follow an exponential distribution. Okay, so we're going to talk about that and see how do we calculate the average? How do we calculate probabilities? How do we calculate the variance? All the same things we've been talking about for discrete probability distributions, and with the uniform distribution, we're now going to say, hey, what about exponential? How do we handle those situations? Okay, so here's the lowdown. Let me use this. So here's the lowdown. So if we have a random variable x, so again, in this case, we're talking about the amount of time that passes until an event occurs. Okay? So we're talking about amount of time. Okay? So if this is the case, if that's the scenario, then this is going to be an exponential distribution, which means x exp. Okay? We don't want to use e, right, capital E, because that's used for the expected value, right? So if we use e with some number in parentheses, it would be confusing. So what we do is we use exp for exponential. And then inside here is going to be the parameter. Now in this textbook, again, uses m for the parameter, and I'll discuss what m is in a moment, but also realize that in this textbook, if you go to the back and some of the appendices or in the homework, m is also equal to lambda. So they'll use lambda in this case as well. So lambda can be used in multiple cases for a parameter. It's just what that parameter represents is different. So in this case, we're going to use m. Okay, so now, what is the rate of decay? That's m. M is the rate of decay. So m is the rate of decay, or decay rate, and m is going to be always bigger than 0. It has to be bigger than 0. If it's 0, we don't have an exponential distribution. If we don't have anything. So it has to be bigger than 1, or excuse me, bigger than 0 to have any meaning. Okay? So it could be less than 1, it can be equal to 1, it can be greater than 1, but it can't be 0. Okay. Let's see here. Okay, so now, here's the probability function. So one of the things about the exponential distribution that I'm going to say right off the bat is that there is no function in your calculator to give you these probabilities, especially when we talk about probabilities, or the PDF function. So you have to know these formulas. So the PDF function, f of x, is equal to e to the negative, oh, sorry, hold on, I'm missing a piece here. It's going to be m. Yeah. M times e to the negative m times x. Okay? So it's the decay constant m times e raised to the negative exponent of m times x. Okay? That's the PDF function. Okay? Now, to get the cumulative distribution function, okay, we have to integrate using calculus this function, okay? But we have the formula. So the PDF function, there's two formulas, but if you know one of the formulas, all you have to do is remember the complement rule to get the other one, okay? So the CDF function for probability, right, cumulative density function, is going to be equal to, well, which we're going to, probability of x less than or equal to x is going to be this. 1 minus the probability of x greater than or equal to x. Okay? Well, this is the one you're going to have to know. This one. So it's going to be equal to 1 minus, it's going to be just e to the negative mx. That's all it's going to be. Okay? So if you remember this function here, the probability of being greater than or equal to x is just e to the negative mx, then use the complement rule to get this one. Okay? So that's the way I would do it. Just remember this probability. So let me do this. So it'll make it easier to see. So this probability is just equal to this piece right here. So if you just remember that this probability is just e to the negative m times x, then use the complement rule to get this one. That's all you have to remember. Okay? Now there's no function on the calculator, so you have to know these formulas. There's just no way around it. Okay? So now, what about the average? Well, here's the general for mu and variance and standard deviation. Oh, by the way, again, you could just use greater than or equal to, right? Continuous, it doesn't matter. But again, keep in mind. So now, what about the average, right? Mu. So for an exponential distribution, for mu, it's going to be 1 over the decay constant. So the average of an exponential the expected value of x, right? If x is exponential, so again, x, okay, is going to be just 1 over m. Just the reciprocal of the decay constant, okay? The rate of decay. So mu is always going to be 1 over m, okay? Now, the variance, now here's the thing. The variance is what? It's going to be equal to mu squared. Okay? Well, what does that mean? Sigma is just going to be equal to the mean. So the standard deviation is always the same as the mean. Okay? Well, in other words, 1 over m, and this will just be 1 over m squared. So notice how, again, just like all the other distributions, as long as we know the parameter, right? We know the distribution, we know the parameter, we can get everything using just the parameter. So just remember this, okay? So if we know that mu is equal to 1 over m, then we also know that, and the other thing too is knowing that mu and the standard deviation, the mean and the standard deviation are always the same for an exponential distribution, okay? Yeah, so that's all that you need to know for this one. So anything else? Oh, one other thing too that I wanted to let you guys know. So also with an exponential distribution, percentile, okay? Here's a formula that you want to know for finding the kth percentile, okay? So for the kth percentile, all you're going to do is take the natural log of the area to the right. Okay? To the right of whatever the value of x that you're looking for. Okay? And then you're just going to divide it by negative m. Okay? Or you can also write it this way too. This would be the same as the natural log of the area to the right, right? And then what is negative m? Well, it's the same as 1 over mu, right? Well, this is just going to be the same as negative mu times the natural log of the area to the right. Okay, so either one will work. The textbook gives us this one, right? So you could use this one. So, but what if you know the average? What if it gives you the average? You can do this too. Okay, they're the same formula. Okay, so just again, just something to keep in mind. Now the thing is this is if you want to find the x value. So here you're looking for the x value. Right? So you're looking for the x value that represents the kth percentile. Okay? Well, how do you do that? Well, let's use an example. Let's say I'm interested in finding the x value that represents the 75th percentile. Well, what do we know about the 75th percentile? Well, we know that the percentage of values that are at or below that value, whatever that value is is what? 75%. Which means if we think about area, that means the area to the left is what? It has to be 0.75. So if that's the area to the left, what's the area to the right? Well, it has to add up to 1, right? So that means use the complement rule. So that means the area to the right has to be 0.25. So that's what you would put in here. And then you would take the natural log of 0.25 divided by the negative value of m, the decay constant, or the rate of decay. That's it. Okay? And so that's the last formula that you're going to want to know to answer any questions regarding an exponential distribution. So let's do some examples. So now, let's say, I'm going to do an example here. Let me see if there's another example I like. Oh, here we go. Let's do this one first. So it says here, on average, a pair of running shoes can last 18 months if used every day. The length of time running shoes lasts is exponentially distributed. What is the probability that a pair of running shoes last more than 15 months? Ooh, nice one. That's a nice one. Okay, so let's do that. Okay, so what do they tell us first? It says, on average, a pair of running shoes lasts 18 months if used every day. Okay? What is that value? That's your mu, right? So on average, right? So mu is 18 months. Okay, good. So we got that down. The length of time running shoes lasts is exponentially distributed. So what's x? X is the amount of time until your shoes fail, right? Makes sense, right? So x is exponential. Now, what does m equal? Well, m, think about it. Let's use mu, right? So we know that what? Mu equals 1 over m. Well, what does that mean about m? M equals 1 over mu. So m equals 1 over 18. Okay, so now we got everything we need. So now, let's answer the question. What is the probability that a randomly selected pair of shoes, running shoes, will last more than 15 months? So more than, x lasts more than 15 months. Well, so what's the formula that we're going to use? Well, the formula is going to be e to the negative mx, right? Well, what's m? M is 1 over 18. What's x? X is 15. So this is just going to be e to the negative what? 15 over 18, right? Does that make sense? So now I know what I'm going to do. I'm going to stick this in my calculator. So there's an e to the x key on your calculator, or e to the y, I'm not sure which one. But if you use this key on your calculator, you can just put in negative. Make sure you use the negative key on your calculator, not the subtraction key. Okay? You'll get an error. Okay? So let's do that. So let's go to e to the x. So we're going to do second, and it's your natural log key, by the way. So do second natural log to get your e to the x key. Now I'm going to put in negative 15 over 18. So negative 15 divided by 18, and then hit enter, and I get 0.435. So the answer is 0.435, and I'm done. That's it. So the probability that a randomly selected pair of running shoes, if they're used every day, will last more than 15 months is 0.435. Okay? So not a bad probability. Okay? That's pretty good the last 15 months if you're running every day. Okay, so now, let's say that it says, here's the next one. It says, on average, how long would 6 pairs of running shoes last if they were used one after another? So that means you're going to use one pair of shoes every day until they break down. And then you're going to get the next pair of shoes, and they're going to use those every day until they wear out, and so on and so forth. How long would you expect the 6 pairs of shoes to last? Well, think about it. How long do we expect one pair of shoes to last if used every day? 18 months. So how long do you think we would expect 6 pairs of shoes to last if we use them one after another until each pair wore out? 6 times 18 months. So that's it. So the amount of time is just going to be mu times 6. So it's going to be 18 times 6. So what is it? $108. So 108 months is the answer. Any questions about that? Good. Okay, so now 108 months is how long you would expect 6 pairs of running shoes to last. So now here's another thing. Here's another question. It says 80% of running shoes last at most how long if used every day? 80% of shoes will last at most how many months? Okay, well, what does that 80% represent? A percentile. So what they're saying is 80%, right? So let's draw this. This is great. So let's draw this out. What's the function? Well, f of x equals what? Negative m e to the negative m times x. So this is going to be what? 1 over 18 times e to the negative 1 over 18 times x, or x over 18. So negative x over 18. So now, how do we draw this, by the way? Well, let's draw this out so we get an idea. So an exponential curve starts high and decreases. It's a decreasing curve. So now, because why? In this, it's always negative. Okay? So now, here's the thing. What's the highest that this will be? Well, when x is 0, right? We're talking about time. Where does time always start? At 0. Okay? So it goes from 0 to infinity. So what happens at 0? Well, when x is 0, this exponent is 0. What's any number raised to the 0 power? 1. So e to the 0 is 1. So all we end up with is 1 over 18. So that's where it starts, and then it just does something like this. Okay? So now, this is what it looks like. So what we're looking for is the time, the x value, where the percentile is the what? The 80th percentile, right? Because they're looking at the point, the number of months where 80% of the shoes will at most last as long. 80%. So at most means equal to or less than, right? So that means this area right here. This area has to equal 0.80. Right? Area, percentile. Okay? So now, what do we do with that? Well, just like we did with the uniform distribution and a percentile, we're going to use the formula for a percentile. Except, in this case, we actually have a formula that we can use to give it to us directly. Okay? So remember, for the kth percentile, right? So this is our x. That's going to be equal to the natural log of area to the right divided by negative n. So let's use this. This will give us our number of months directly. So now all we have to do is plug in the area to the right. What's the area to the right? Well, if the area to the left is 0.8, the area to the right, or did I say that right? The area to the left is 0.8, the area to the right is 0.2. So it's going to be the natural log of 0.2 divided by the negative m. What's m? 1 over 18. So it's going to be negative 1 over 18. And so what is the x value? What is the number of months that represent the 80th percentile? It is going to be 28.97, or if we round that to the nearest decimal, that's going to be 29.0 months. So we get approximately 29 months. So if your shoes last 29 months, then your pair of shoes, or those particular pair of shoes, are at the 80th percentile of all running shoes, like these. Okay? And that's it. Any questions on that? Okay. Well, let's look at this here. Okay, let's do this. Here's another one. Here it says, let's see. The time spent waiting between events is often modeled using exponential distribution. For example, suppose that an average of 30 customers per hour arrive at a store, and the time between arrivals is exponentially distributed. So again, let me read that. For example, suppose that an average of 30 customers per hour arrive at a store, and that the time between arrivals, okay, so as soon as one customer arrives, the amount of time until the next customer arrives is exponentially distributed. Okay, so let's write that down. So what does it mean? It says the average of 30 customers per hour arrive at a store. That's mu, right? So in this case, we know mu is equal to 30 customers per hour. What is m? M is 1 over mu, which is 1/30th. Okay? So now, what do we know? We know x, the amount of time that passes after one customer has arrived until the next customer is exponential. So it's going to be exponential with m equal to 1 over 30. Okay, so now, on average, how many minutes elapse between two successive arrivals? So think about this, two successive arrivals. Well, after the first arrival, the amount of time is what? So as soon as the first arrival occurs, the amount of time until the second arrival is what? Well, an average of what? Well, it's 30 customers per hour. So on average, how much time is between customers? Well, it's going to be what? Well, how much time is going to pass on average between the two customers? You're going to divide this into, we're going to have to do minutes, right? Okay. So how many minutes are going to elapse? Well, this is going to be 60 minutes. So what is it? Half a minute, right? So for part A, how much time on average? Well, on average, it's 30 customers per hour, right? So mu is equal to 30 customers per hour, which is going to equal 30 customers for every 60 minutes, which is going to be a half a customer a minute, or no, not a half, a half a customer per minute, right? So this is going to be 1 customer for every 2 minutes. Okay, so how many minutes will pass when you have 2 successive customers? Well, think about it this way. If I have the first customer, well then how much time is going to be there until the second customer? It's only going to be 2 minutes. So the answer is going to be 2 minutes. So the time from one customer to the next, 2 successive customers, is 2 minutes. Okay? Okay, that's it. That's the answer. So B. Now B says, when the store first opens, how long on average does it take for 3 customers to arrive? Ooh, so here, if it takes 2 minutes between customers, how long do you think that it's going to take for the first 3 customers to arrive? Well, let's say I go to the store window, the store door, and I flip the sign from closed to open. Well, how much time is going to pass until my first customer arrives? 2 minutes. And then the second customer, from the time that the first customer arrives, 2 minutes. On average, it's going to take 2 minutes for every customer, right? So 2 minutes until the first customer, then another 2 minutes until the second customer once the first customer has arrived, and then 2 minutes on average. Again, these are just averages. So on average, how long should it take for my first 3 customers to arrive once I open the store? 6 minutes. Does that make sense? I hope so. Okay, so let's think about this. So on average, it would be 6 minutes. if you just think about it. 2 minutes for each customer. Okay, now what about C? So I'm going to erase this here. So what about C? C says, after a customer arrives, find the probability that it takes less than 1 minute for the next customer to arrive. So think about this. As soon as one customer arrives, again, the time starts over, right? So now they're saying, what's the probability that the next person arrives in less than, what is it? Less than 1 minute. Okay, so the probability that X, now again, what is X? X is going to be, we're counting the number of minutes, right? So M, again, this is where we're going to have to, M is 1 over 30, but if we change this to minutes, right? Because that's the time increment that we're using, minutes. It's going to be what? 0.5 customers per minute. That's mu. So what's M? Two minutes. Okay? Does that make sense? So always make sure that you have your average in terms of the time increments. Okay? Because that's what everything else is going to be done in. Okay? So you just have to read the problem carefully and make sure you got things matched up. Okay, so now we know M is 2 minutes, right? Because it's reciprocal. So if we go back to here, then 1 over mu is equal to 1 over 0.5, which is 2. Okay, 2 what? 2 minutes. Okay, that's the decay rate. Okay, now, going back to the problem, it says, what's the probability that X is going to be less than 1 minute? Well, the formula that we're going to use, because it's exponential, is going to be 1 minus the probability of X greater than 1, which is going to be 1 minus e to the negative mx. And so now we just plug, right? So this is 1 minus e to the negative 2 times what? What's x? Oh, hold on a second. Yeah, yep, that's right. So x is going to be 2. So now, oh, hold on a second, I did something wrong. Hold on. Did I do that right? Yeah, that's right. So M hold on a second. So the average number of customers per minute. So one customer every 2 minutes. Let me think here. So I made a mistake. How am I? So I got that right. Yeah, because this doesn't make sense that this would be 2 minutes. Two minutes per customer. Oh, yeah, I do have this backwards. I'm sorry, yeah. Mu, sometimes I have a brain fart. Sorry about this. So think of it, what are we measuring? What's x? It's time, okay? So you've got to think about, when we talk about mu is an average amount of time. So when I said mu is customers per hour, that shouldn't even made sense because it's not time, that's customers. So this can't be mu. This is the decay rate, M. M is the number of customers per hour. That's the rate of customers, okay? The time, the average amount of time is 1 over M, which is 2 minutes. So I have these backwards. That's why it wasn't making sense when I was looking at this. So this here, now this is going to make sense. So now M is 0.5. Okay? So now X is 1 minute. Okay? So now it makes sense. So here M is 0.5, and so, right, so 0.5, so that's the rate, customers per minute, that's the rate. The average amount of time between customers is 2 minutes, okay, which is right. So everything else for A and B is correct, except for my notation, I got that switched. So C is here. So the probability that X is less than 1 minute, the amount of time that passes until the next customer, the probability that that amount of time is less than 1 minute is this. Okay, so now we just plug and chug. So it's going to be 1 minus what? E to the negative, that's negative. E to the negative 0.5 times 1. So it's going to be e to the negative 0.5. So 1 minus, and it's going to be 0.393. Oh, hold on a second. 607. So this is 607, right? So this piece is 0.607, and then we get 0.393. And that's the probability. So again, let me go through that one more time, okay? So part A, it said on average, how many minutes elapsed between 2 successive arrivals? So what's the average amount of time from one customer to the next customer? That's mu. So the average amount of time is going to be now what do they give us? They give us the rate of the customers. What's the rate of the customers coming into the store? That's M. 30 customers per hour, or 60 minutes. So that's 0.5 customers, or a half a customer a minute, or 1 customer every 2 minutes. That's the rate. Now, we're going to use the formula of 1 over the rate to find the average amount of time per customer, which we already know is 2, right? 2 minutes. That's the answer. Now, we can know this. Now that we got this correct, now we know that this is the exponential distribution. And then B is when the store opens, how long is it going to take for the first 3 customers to arrive? Well, it's going to be an average of 2 minutes for each customer. Again, we get the same answer, 6. Okay? Then for C, the probability that after 1 customer arrives, what's the probability that the amount of time for the next customer will be less than a minute? Well, that's what this calculation is. Okay? Now, D says after a customer arrives, find the probability that it takes more than 5 minutes for the next customer to arrive. So now D, not B, D says, what's the probability that X, after a customer arrives, that the amount of time that will elapse until the next customer arrives is more than 5 minutes? Well, now, all we're going to do is we're going to use the formula e to the negative m times x, where x now is 5. So this will just be e to the negative, what is m? 0.5 times x, which is 5. And so now, what does this probability equal? Well, let's find out. .082. 0.082. That's it. That's the probability that the next person arrives, the next customer arrives, or the probability that the next customer arrives, let me say that again. The probability that the amount of time that elapses till the next customer is greater than 5 minutes is very small, 0.082. Okay? So unlikely that it'll take that long. Okay. Now, E. Oops. Okay. So E says 70% of customers arrive within how many minutes of the previous customer? So let's do this. Okay, so E, let's set up draw our diagram, right? So we know it's going to look something like that, right? So again, we have, it's going to be f of x is going to equal negative m to the e to the negative mx, right? Well, m is 0.5, so it's going to be negative 0.5, or a half. You can even write it this way too. So it's going to be negative 1/2 times e to the negative 1/2 times x. So, when, again, this is minutes, so 0 to infinity. So when x is 0, we get a half. Or excuse me, nope, that's not negative. That's positive, sorry. So it's going to be a half, right? So now, we know it looks like this. So what are we looking for? We're looking for the cutoff for x. So we're looking for the number of minutes where 80%, or no, is it 80? 70%. Where 70% of all customers arrive in less time than that after one customer has arrived. Okay? So this area to the left has to equal 0.70. So now what we're going to do is we're going to set up the formula again. So probability of x less than whatever that value is has to equal 0.7. Well, we already have the formula for that, right? So what's the formula? It's going to be the kth percentile equals, so this is x again, right? Equals the natural log of the area to the right, or, yeah, to the right, divided by negative n. Well, what's the area to the right? Well, if the area to the left is 0.7, the area to the right has to be 0.3. So this is going to be 0.3, and what's m? M is 1/2. So this is what we're going to do. So let's calculate that. So it's going to be the natural log of 0.3 divided by negative 0.5, and it's 2.41. So 2.41 minutes. So the amount of time that elapses that represents the 70th percentile is 2.41 minutes. That's it. And let's see here. Now, here's the thing. Now, again, we're not going to be tested on this, but let's talk about the reasonableness of this being an exponential distribution. Is it reasonable to believe that customers arrive, the amount of time between customers is exponential? Think about it. This scenario assumes that customers are arriving one at a time. Does that happen in real life? Well, no, not really. Customers arrive together in groups, right? Husband and wives, families, kids, right, with parents. So it might not be reasonable that this would follow an exponential distribution. So think about this. Let's see here. Oh, this is the other thing too. Is it always the case that this rate is constant? Right? This assumes that